Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be concluding Chapter 2 on one-sample tests. I've scrolled on down. Here we are at one-sample tests, and the video links are here. The R code is here. Let's jump over to the notes. So the mechanics of setting up a hypothesis test are important to understand. And so you should imagine when you're setting up a hypothesis test that you are the researcher conducting the experiment. In our class, you will often be analyzing data that other people have collected, and but in practice, you may sometimes have the opportunity to be collecting data to answer your own research questions. So in many cases, we want to establish whether there's a change from the status quo. Okay, and the status quo is summarized in the null hypothesis. And so H0, our null hypothesis, is what we'll consider the status quo. And the alternative is really the research hypothesis. That is the thing that's when something interesting has happened, when something different from the status quo has happened. In some cases, the null hypothesis will be, for example, say you go to the doctor and you have a test, say whether you've got high blood pressure or something, and if you're within a certain normal range, that will be status quo. Otherwise, if you say have high blood pressure or very low blood pressure, then you might need to take action and do something different, like take medication, change your behavior, something like that. And so that would be the alternative, is when you actually do something, when something interesting is happening. All right. So the mechanics behind a test sort of fall in this table. So there is a state of nature. Either the null hypothesis is actually true or it's actually false. Okay, so we're going to consider the state of nature as being what's the truth. Okay, and often because we're specifying a null hypothesis of the true population mean equals a very specific value, like in our age, the mean age of heart transplant was 50 years. Chances are it's not actually equal to exactly 50, but the point is that it's we didn't have evidence that it was different from 50. So in most cases, the null hypothesis won't actually be true, but it sort of stands in for a plausible value. Okay? And then when we conduct our hypothesis, we either fail to reject the null, which is that the data were consistent with the null hypothesis, or we reject the null, which indicates the data were supported the alternative hypothesis. Okay, and so in here, in the body of this table, indicates what happens. All right, so if the state of nature was actually that the null hypothesis was true, and we failed to reject it, then we made the correct decision. Wonderful. If the alternative was true, and we rejected the null, then we also made a correct decision. But as you can see, that there's two ways of making an error. The first type is when we assume the null hypothesis is true, which is what we do when we conduct a hypothesis test, but we got an unusual sample that caused us to reject the null erroneously. And in that case, the null was true, we rejected it, we made a type 1 error. The alternative is when the alternative is actually true, but we got a sample that actually supported the null hypothesis, or we didn't have enough evidence in our data to actually reject it. So in that case, the alternative was true, we failed to reject the null, and so that is a type 2 error. And the probabilities of making errors are given Greek letters. So the type 1 error is called alpha. That's the probability of rejecting the null when it's actually true. So that's the probability of type 1 error. Beta is the probability of making a type 2 error. That's when we fail to reject the null, but the alternative was true. And there's another value called power, which we'll talk about a little bit later. So in practice, we often set alpha to be a certain value, such as 0.05. So that's we specify the type 1 error. And then the type 2 error then is determined based on our sample size and other characteristics of the population, such as the variability. All right, so that's what a lot of this says. I suggest that you read through that. I'm going to skim through this. I recommend that you read it. The basic idea is, what's the effect of alpha on the rejection region of a two-sample test? So basically, if alpha gets small, so from 0.05, if you decrease it, say, to 0.01, the rejection region is going to be 0.01 big, so it's going to be small. And if I page on down, here actually are those two cases. The light gray are the shaded regions left and right are when alpha equals 0.05. So the gray areas going from this line of 2.2 and more extreme, includes this black area, is 0.05, that's alpha. And when alpha is equal to 0.01, then it's this black region, the more extreme region. So alpha is the area of these tails in the rejection region. All right, so I go through an example there as well. And I talk about the relationship between confidence intervals and p-values. So in the case of a t-test, where we're determining the result of testing whether, let me start that sentence again. The relationship between confidence intervals and p-values, there's an equivalence when you do a t-test. So when the sampling distribution is actually normal, so that the t-test is the right procedure, then you can actually determine the result of a t-test by using the confidence interval. And so the relationship goes something like this. Say that you conducted a hypothesis test and you rejected the null hypothesis. Okay, so if you reject the null, that means your t-statistic was fairly extreme. It was different than the null. Now that's consistent with your confidence interval not containing mu naught. Sorry, that wrapped in a strange way. So your confidence interval doesn't contain mu naught. A way of thinking about that in terms of the confidence interval is that if mu naught is not in your interval, then it seems that mu naught is sort of an unlikely value given the data that you saw. Okay, so that's consistent with rejecting that value, that null hypothesized value. Similarly, the p-value would be less than alpha. Okay, that less than alpha caused us to reject the null. So all those sort of go together. And similarly, you can look at it in the other direction. If the null hypothesis was not rejected, then the p-value must have been larger than alpha, and it will turn out that the mu naught value will be inside of your confidence interval, meaning mu naught is a likely value. Okay, so mu naught, yeah. Rewind and play me again if you want to hear it again. I won't repeat it. All right, so here's sort of that example. The t critical value here is, so the gray region here is our rejection region if we were to do a hypothesis test. And so if we got a t statistic that was inside this white area is effectively like our confidence interval. Okay, so if you got a t statistic that wasn't very extreme, then our confidence interval would have contained the null hypothesized value, and our p-value would be quite large. Okay, but if you end up out in the tail, then we would reject, and the null hypothesized value would be outside of our confidence interval. All right, so that's what all that says. At the end of the day, you have to make a decision about what's important. And statistical significance is not the same as practical significance. In fact, let's see, we're on page 35. I'm going to page up to the very top of the document, and I'm going to page down until I see the formula for a confidence interval. Looks like I'm getting pretty close or have passed it. All right, let's do this. All right, so here we are at section 2.2. All right, so what happens to a confidence interval as our sample size gets very, very large, say 10,000, 100,000, a million? Okay, what happens? Well, the form of our confidence interval looks like this. It's the sample mean plus or minus a t-statistic, which is going to be roughly 2, times the standard error. And the standard error depends on the sample standard deviation, which is an estimate of the population standard deviation, divided by the square root of n. So as n goes to infinity, this ratio, which is divided by n, the square root of n, goes to 0, which means this standard error goes to 0, so this whole quantity is getting multiplied by 0, and so we have a sample mean plus or minus something that is going to 0. Maybe so our confidence interval is getting narrower and narrower and narrower. Okay, the probability then that it's going to contain a hypothesized value also goes to 0 because our interval gets infinitesimally wide. If I scroll down to a hypothesis test and look at this t-statistic, so here's our sample mean minus our hypothesized mean. So whatever that difference is divided by a standard error. And this standard error is going to 0. So if this denominator gets close to 0, then this ratio that's being divided by a number close to 0 gets very large, goes to infinity, basically. And so this t-statistics gets very, very large. And that, if it starts to get greater than 2, then we're going to reject the null hypothesis. So as our sample size goes to infinity, the standard error goes to 0, the t-statistic goes to infinity. So just by having a very large sample size, you become almost certain to reject your null hypothesis. So let me jump back down to practical significance. So the point is that you may have statistical significance and you reject the null hypothesis. Okay, so a t-test is significant. You have a statistically significant result if you reject the null hypothesis. And so you may reject the null, but you may, the actual practical significance could be very, very small. All right, so there was an example that I skipped in the video about this Tocopilla meteorite, and we asked whether the hypothesized mean was that the true population mean was 0.54, and that was in support of some cosmological model about how meteorites cool. When we calculated our confidence interval, we found it to be from 0.55 to 0.58. So it did not include the null hypothesized value. So we reject the null hypothesis that this is the correct value for the mean in favor of the alternative that in fact the mean is different from 0.54. But now we have to decide whether this has any practical significance, meaning is the data supports a value from 0.55 to 0.58 for the mean, Is that very much different from 0.54? It's only, a couple hundredths away. Now, I can't answer that because I don't know anything about meteorites in terms of this particular problem. But it could be that there's different competing models out there. One model says the mean should be 0.54. Another one says it should be 0.56, in which case that seems like maybe the second model is correct. And there might be a third model that says the mean equals 3. In which case, if you're comparing model 1 to model 3, this is the data supported the model 1, even though it doesn't actually support it perfectly. It was statistically different, but maybe not practically different. Okay, so as a context expert in your field conducting hypothesis test, you need to be smarter than the statistical test and decide, is this actually a difference worth worrying about in the context of the problem? Or maybe it's not, because I have a huge sample size, and of course I'm going to reject the null hypothesis. Okay, so that is all up to you. The last section here discusses power, and the power is defined as the probability of making the correct decision when the true state of nature is the alternative hypothesis. So this is the probability of correctly rejecting the null hypothesis. Here is the sentence I was looking for. So if the null hypothesis is actually false and you correctly reject the null, then you have made a correct decision. And the probability of making that decision is the power. And there's a package in R called PWR, power, for calculating the power of a hypothesis test. There's other packages as well for more specialized cases than t-tests. And so I encourage you to learn a little bit about that for your own research. The rest of this chapter has to do with one-sided t-tests. This is all review from Stat 145, so I'm going to give you the opportunity to read that. The main difference here is that when you are looking to reject, rather than having a rejection region on both sides, the rejection region is on the side of the alternative. So for example, if our alternative hypothesis, if I page up for a moment, so we have a null hypothesis which is equal, and the alternative, let's take the second case of the upper one-sided. The alternative here is that the true population mean is actually greater than the alternative. So this might be a case where, say, you're feeding your plants fertilizer and you want to know if the average growth is more than the status quo of your null hypothesis. So in that case, we would have a one-sided alternative because we're interested if it makes it grow more. It occurs to me that maybe we actually might want to worry about if it actually hindered growth, but in this case I'm actually just thinking about helping growth. So in that case, the rejection region is only going to be on the right-hand side. This has some real big advantages. One is this rejection region on the right is bigger. It means you need slightly less evidence if you've made the correct guess about which tail your data is going to support, either the upper tail or the lower tail. So that was the upper, and this is the lower less than alternative down here. All right, there's an example having to do with canned tomatoes, about whether the weights of those tomatoes are what actually we see on the label. And then also calculations of one-sided confidence intervals. I encourage you to read through that. And that is everything for Chapter 2. Thanks so much for listening all the way through. These lectures are basically as long as they would be if I was lecturing in person. And so spending this time is effectively like being in class for lecture. The advantage, of course, being that when you're in class, we're actually doing activities instead of you struggling at home all by yourself. So I hope you appreciate that flipped classroom atmosphere, and join me in a little bit for Chapter 3.